Good morning, this is Dr. Turner for Integrated Math 2. Today we're going to be covering 6.2, which is looking at similar polygons. Again, in 6.1 we talked about dilations, which are a type of transformation that will create similar figures. With similarity, we are generating a figure that has the same shape but a different size. That's opposed to congruency, which has the same shape and the same size. So in 6.2, what we're looking at is what is the relationship, first of all, between two similar figures, and what are some of the ways that we can show that they are similar? Just like with congruency, where we had different theorems, angle, side, etc., we're going to have similar theories for angle, triangle, or polygon similarity. We're going to focus on triangles, but really these principles can be applied to any set of polygons. So we'll start out just looking at what is the relationship between sides and similar polygons, and what is the relationship between angles and similar polygons. So in similarity, and let's focus on triangles because that's what we're going to be focusing on here in our section. For two triangles to be similar, our angles all have to be the same. So all the angles between the two shapes have to be congruent. Remember that equal sign with a little squiggle above it as your congruency symbol. The sides have to be proportional. So if I divide any two pairs of sides to get the ratio, which we did in 6.1 talking about dilations, that ratio has to be the same for any two or any pair of sides that I choose. All the sides have to have that same proportion. So the first couple questions in your assignment are going to ask you that. What's the relationship of angles and similar polygons? They're congruent. And what's the relationship between sides and similar polygons? They are proportional. So there's a couple things that we could do with this. One, you might be simply given a triangle, let's say 3, 4, 5, and the same triangle, 6, 8, or similar triangle, 6, 8, 10, and be asked to just justify, are these two triangles similar? Why or why not? Again, we'll get into the specifics of how you can prove that in 6.3 through 6.5. But for now, and again, I might be given the angles, I might not. I might be given the coordinates. Again, I'll stick with ABC and ABC prime. But you may not be given those vertices. You may not be given labels. So the goal then is to see, okay, if these triangles are oriented the same way, in which I drew them, they're both facing up, if you will. I want to verify that they are similar by looking at the proportion of the sides. So I'm looking at corresponding sides, the sides that look to be the same, right? Same shape but different size. And so if I, let's say, take 6 divided by 3, that gives me a scale factor of 2. And I would need to check the other sides. 8 divided by 4 also gives me a scale factor of 2. 10 divided by 5 gives me a scale factor of 2. So because all of those factors, all those ratios match up, I can say without a doubt that yes, these triangles are similar. Same shape, but different size. I could also verify that with the angles, but again, we'll get into a little more specifics with that as we get into 6.3 through 6.5. For now, we just want to be able to look at two triangles and justify that they are similar by showing that the sides are proportional. This is used a lot when you're dealing with scale models. So some problems might give you one measurement of a model and its corresponding actual length, and then look at another measurement and try to determine either A, what the length is on the model, or B, what the length is on the actual figure. So, for instance, let's say, and we'll type this out here, model car measures, let's say, 3 inches wide by 8 inches long. The actual car has a length of 12 feet. What's the width? Okay, so we're given the measurements of the model, and we're missing one of the measurements of the actual figure. And let's make this big so we can actually see it. So this is a cross multiplication problem. We're assuming that these are similar. I'm assuming that the model is built to scale. So it should be proportional then. It should be a similar figure. So start out, and you can do this a number of ways, but I'm going to start out and write out that for the model, the length is 8 inches on the model. On the actual car, it's 12 feet. And then the width is 3 inches. I want to know what the width is in the actual car. So I'm setting up this proportion, and then I can cross multiply this to solve for my variable. However, remember that when you're cross multiplying, you need to make sure that your units match up. So on the left side I have inches, and on the right side I have feet. I don't want to leave it like that because it'll end up getting messy. So I can either convert the feet to inches, or I can convert the inches to feet. I'm going to go ahead and convert the 12 feet to inches. So there's 12 inches in a foot. I would multiply that by 12 to give me 144 inches. Now this is something I can cross multiply, so I have 8 times x, and then 144 times 3, and you can use a calculator if you need to. Should be 438. Then I'm going to divide both sides by 8. And this gives me x equals 8 into 430. That's going to give me 53.75. You can verify that with a calculator. This is inches. I could leave it like that if I want to, but because the original car length, or the actual car length, was 12 feet, I probably want to convert that so that it's in terms of feet also. So if I want to do that, I would do 53.75 divided by 12, but again, that's optional. Otherwise, I can leave it as is, but that gives me 4 feet and 5.75 inches. Okay. Because this is a word problem, of course, I would want to answer that in a complete sentence. As we've mentioned before with word problems, it doesn't have to be a long sentence, but it does need to be a complete one. Okay. So those are types of problems where you will be using cross multiplication. If you are given, again, 2 measurements of one shape, but you're missing one of another shape. Okay. Other problems that you can be given are simply to show you 2 measurements for one figure with one missing on the other figure. So it doesn't have to be triangles, but we'll focus primarily on triangles. Let's say I have 7 inches, 3 inches, 8 inches, and in the other triangle I have 10 inches, and I want to solve for this side. Now, typically if we're doing problems, I try to give you guys questions that will give you a whole number or an integer as your answer. That won't always be the case with similar figures. It's very common to get a decimal. And so if that's the case, it'll tell you, or it'll specify round to the nearest blank, the nearest hundredths place or to 3 decimal places. So pay attention to what the directions are saying. Here you want to set up figures, set up the sides that are similar. So 7 is to 10, as 3 is to x. So I'm lining up my corresponding sides. Then it's cross multiplication, 7 times x, 3 times 10. Divide by 7. And again, depending on the directions, it might say that you can leave it as a fraction. Otherwise, what you would need to do is you would need to go in and look at the decimal. So let's say we use Desmos as our calculator, and I'm just doing 30 divided by 7 to get an accurate decimal. 30 divided by 7, round to the 3 decimal places, that would be 4.286. So those are the 3 types of problems that you'll encounter in your 6.2 assignment. That's it for today. If you have any questions, please reach out to me. Otherwise, have a good day, and I will talk to you soon. Bye.